So our speaker today is Boris Tsygan. His talk is titled A Review of Non-Commutative Forms. Please, Boris, go ahead.
Okay, so there will be little new in this talk. It's partly, came out of writing a book chapter, but there will be something new, and I will point out when it is. So maybe I would say there will be some new statement and maybe a couple of questions. So non-commutative forms for an. By the way, do I have an hour or 50 minutes?
Yeah, 50 minutes. And
50 minutes. Yeah. So an associative algebra over K, and K is a commutative unital ring, mainly, probably not always, but mainly in characteristic 0. And I think even it's credited to Arveson, I think, around Kuhn's introduction of non-commutative differential geometry in the early 80s. Arveson, Kuhn, Karoubi. So you generate an algebra by A, which you view as a subalgebra, and K module D, which you write as A over K, or A over K times 1. And maybe let me, for the future, say that you denote this reduced thing by A bar. It's just a K submodule, and you introduce relations.
Sorry, your A is unital too, not just K.
Yeah. Unital algebra over a unital ring, yeah. And you introduce this relation. And then, there is this thing you do not introduce. I had my daughter over from Stockholm, and just yesterday, and she's a teacher, and she was asking me, how do I teach change of variables in double integrals? And I say, well, I showed her basically, determinant and this relation. And she says, I doubt my students will appreciate that. And I say, you know what, on Tuesday, I will be giving a talk how to avoid that. So everybody, you can tell them that they are welcome to join. And so I am not assuming that, and that would be not, of course, not natural for non-commutative algebras. So that's it. And the advantage is that it's very simple. The disadvantage is that the cohomology is not very interesting. By the way, so it is universal among those that, so this is an algebra, of course, fixed algebra A, and this is morphism of algebras, and this is a differential graded algebra. And it's universal among such And what's the differential graded algebra? Differential graded algebra, this is how it is defined. Okay, and a small lemma says that there is a natural map and again, grading is of course by number of days. And the morphism, as I would say, is the naive HKR. This is this map as well, kind of probably what inspired Kohn a lot in introducing cyclic homology. And it happens to be an isomorphism. So this is the lemma. And well, one proves it by, of course, by, I would say, it's obviously surjective because any time you see those in the wrong position, you can exchange them using the relation. And then you see that actually you can happily multiply the left-hand side or have a product on the left-hand side. And therefore, by universality, you are okay. Okay, so, and in particular, so if you look at the what does the Ram differential intertwine with, you see that it's a very, very simple thing. It's just tensor multiplication by 1 on the left. So this doesn't even this differential graded algebra it does, of course, remember multiplication in A. A is a subalgebra, but the differential, the de Rham cohomology, doesn't even know the multiplication. It's just pure linear algebra. And the non-commutative Poincare lemma just says that basically it's acyclic. Apart from K, from the scalars, it's completely contractible. But not in a canonical way, which is important. Okay, so it has some silver lining in it, which I will mention later, but probably Karoubi, maybe Kohn too. define non-commutative de Rham complex by quotienting, factoring out the commutators, of course, the linear span of commutators. Commutators, which makes a lot of sense in differential geometry. Usually, those are matrix valued forms, first example of non-commutative forms. And when you do trace, you get this. And Karoubi in the 80s, I probably won't formulate it, but I will show one of the goals of this talk is a new proof of that. And this leads me, so for now, this leads me to cyclic homology. And I am sure you all know, let me just organize it in a suitable way. So maybe and again, maybe I would stress that this is that I can identify them by sort of naive or basic HKR. And let me draw this picture. As we all know, there are two differentials. One is the Hochschild differential and one is the cyclic differential, capital B. So they occupy half plane, kind of, if the plane is cut horizontally. So here we are. This is big B and this is little b. Okay, and what you have here, it's a periodic cyclic complex. Now, maybe, so I can cut it several ways, and maybe so I can cut it like this, and it will be the cyclic complex, which computes the cyclic homology. Or I can cut it, kind of take the complement to that, so to speak. And this will be the negative cyclic complex, which computes the negative cyclic homology. And the entire thing, of course, the periodic cyclic homology. And well, as we know, the diagonals should be, they are infinite diagonals, not finite diagonals.
Isn't it exactly, I mean,
Pardon?
isn't the negative cyclic homology on the left and the positive on the right?
Oh, well, maybe people draw differentials differently. I am used to write capital B from left to right. I mean, maybe if you...
Yeah. Okay.
Yeah, I am sorry. It's a many kind of decade-long tick, so to speak, for me. Yeah, it's hard for me to... Yeah, sorry about that. Okay, and my aim is to point out, and it's not a new thing, and you tell me, people tell me that they are kind of surprised by it. It's a little bit of a hidden gem, but probably also. So you could also go this way. And I'm not sure even what is the accepted notation. It's it's called CD, but what does it mean? You factor out, I mean, you factor out on the top. So maybe let me. So it's just like what I said, but the top is kind of cropped or truncated. And I think it's sort of, I don't know, cyclic deram or something of introduced, I think, correct me if I'm wrong, but by Ginzburg-Schedler. And this is actually a good, so maybe I will just say that first of all, you know, it's so this is this double complex, and maybe in characteristic 0, there is also a non-commutative Poincare lemma for capital B. It also, by the way, it's a thing very much related to or reminding of small b, or resembling rather small d with some modification. And it's also acyclic in characteristic 0 only, because some permutations are involved, summation over permutations. And by the way, the diagonals in this Ginzburg-Schedler complex, diagonals are finite. So again, modulo scalars, the reduced thing is just isomorphic to this complex. And by the way, the cyclic complex is again quasi-isomorphic. Again, modulo scalars, it's a little bit the cyclic complex, again in characteristic 0, is quasi-isomorphic to this modulo scalars. Usually, you know, the original definition was co-kernel of 1 minus cyclic permutation, but this is close. So it's kind of fascinating, you know, a dual version, and self-duality of the cyclic category lambda of con is involved. So I find it kind of cute. Yeah, so in characteristic 0, it's basically the same. And what is its value in characteristic non-zero? Frankly, I'm not sure, but here we are. Okay, so why are we here? Because maybe again, let me say, if you remember the non-commutative de Rham complex, it also has this sort of format. And I'm not sure what you can do in characteristic non-zero, but in characteristic zero, you divide by n factorial, and then this thing intertwines. Oh, sorry, no, this is capital B. Okay, so Ginzburg and Schedler noticed that you could kind of extend it, and I think I noticed it actually in this form. We had a sort of paper together. Okay, so there is this extended HKR from this complex to what? So maybe to extended de Rham complex, and let me describe it next. So first of all, and what is this? This is, well, the same as K with just polynomials in T, just, but just almost free algebra in one variable of degree 0. And, well, the product is clear, is the free amalgamated product, and the differential is the graded derivation. I mean, we already have D, of course, but also we have a graded derivation that sends a dA to 0. No, I'm sorry. It sends A and T to 0. And dA it sends to commutator with T. Okay, and you extend it to a derivation, you can do it. And then you have you immediately observe, from those, from the definitions, on generators that no, it's not a total differential. It has curvature, so to speak, which is an inner derivation. So if you factor the commutators, then by definition you get a non-commutative de Rham complex, and it will be of this form. So, for example, next will be what? It will be and then here you will have so it will be the same format, and it will end on the diagonal by just actually, well, so this diagonal consists of what? I think it consists not of A, but of much bigger thing, namely of this. Okay, so once again, a theorem of Ginzburg-Schedler says that and there is this HKR map, and it's a quasi-isomorphism on every column. Okay, so, yes, and also, of course, maybe I should say that again, all those horizontal things, horizontal differential here, again, you have non-commutative de Rham, non-commutative Poincare lemma. So they are all acyclic modulo scalars. So again, what you see here is just another way of writing the non-commutative de Rham complex, but it gives more of a proof because, well, more of a statement, because you also basically you get a new definition of Hochschild homology, because those columns, apart from the lowest, apart from the top, those columns are the Hochschild homology of your algebra. Okay. So this touches upon a couple of things. Maybe one application of this, or rather maybe, let me say this, there's kind of This thing is already Hochschild. Apart from, I think noncommutative de Rham complex per se is kind of a little bit disjoint from Hochschild homology. There is some resemblance, but this is this already has some Hochschild built into it, and let me explain why. So let me consider the standard bar resolution, and then consider this is D, aka I think D prime in cyclic theory, and this is, I would say, is epsilon. And then kind of consider truncated like this. And this happens to be the differential just becomes iota t that I had defined before. So indeed, you know, so if I replace this tensor product sign by the letter t, I will get exactly okay. So I have this short resolution. It's no resolution at all, of course, apart from free or quasi-free algebras. But then I or maybe should I say that? Then I have this, and this is by definition my extended forms, and then, well, the Rham complex is extended. The Rham complex is the commutator of that. So I would be done if it were the full the full bar resolution, I would know all. And by the way, maybe let me stress another connection. The cohomology would be yes, it would be the Hochschild cohomology, but not of A, rather of A tensor N, and it would be twisted by cyclic shift. But fortunately and crucially, all of it is just the usual Hochschild cohomology by very simple homological fact known as edge-bias subdivision. Okay, so immediately we would get this. Unfortunately, so the idea of this sort of new proof that we give in our book is that ours is not the case. So actually, I would say that actually it happens that our extended Durham complex is more or less precisely with some small variation this construction, but dual. It is applied not to the algebra A, but to the GG coalgebra bar of A. And it looks much bigger than for a couple of reasons, because bar full of anything is bigger than bar short of anything, and bar of A is much bigger than A. So it looks like you are getting a much bigger construction, but well, you know, we are in Hilbert's hotel and things happen, you know, different infinities, you know, may be equal nevertheless. Okay, so this is one, our claim to new things is this new proof of that Ginzburg-Schedler statement. Also, let me just stress that this touches upon a lot of things. So first of all, the thing I have here is very much related to, well, Frobenius, you know, non-commutative Frobenius of Kaledin, but also more immediately, maybe one application of this I think due to Ginzburg-Schedler and Schedler, and then an extended version of Waikit Yeung, that it relates I don't have time, but so if I consider the representation scheme of A, the scheme whose points are d-dimensional representations of A, then there is this Ginzburg-Schedler map from one to another. And again, it could be extended to multi-vectors, and it's important for it's related to Calabi-Yau algebras and categories and so on. Okay, now let me, the remainder of my time, let me try to point out another thing that non-commutative forms versus Czech-Alexander complexes. What's the Czech-Alexander complex? If you have an algebra, maybe, you know, it would be maybe more indicative of to write S instead of K. I don't know why. So this is, for example, and again, maybe note that of course it is acyclic, and it directly projects on non-commutative forms, correct, which are isomorphic to A tensor, A bar tensor, blah, blah, blah. And of course it is acyclic, but and well, in the commutative case, it becomes interesting after some completion. Yes, so for example, well, so you, first of all, maybe you pass to a free commutative algebra, and then you take this and you complete with respect to the ideal, which is the kernel you complete with respect to this kind of diagonal plus kernel, and you get, well, crystalline cohomology and something like that. And Willy Cortiñas, he in non-commutative case, you could do the same thing, but you could also replace tensor product by free product, and then in the spirit of this theory, factor out commutators, and you will get non-commutative crystalline cohomology, which will be identified with periodic cyclic homology. Okay, so my other comment, and I probably I skip a little bit the relation to that one, but maybe I said enough, you know, that one kind of projects to another, is that there is a bigger algebra. There is a little bit of a little bit more algebraic structure. And maybe let me put it this way. So if you have, then obviously, and by the way, I have to use some notation. So if I have a morphism of algebras, then it extends. So this is my whatever version of my Czech-Alexander complex. Now, why is it independent on well, why is crystalline cohomology well defined? Basically, because if you have two, then there is for any two, you have a homotopy between F1 and F2. And maybe let me just write one formula in the commutative case. This is an explicit formula. And you see, basically, I like it very much because it shows the principle how all those differentials do appear in nature. You sort of animate the picture or categorize it. You allow many objects and many morphisms, and then you have some rigid structure. You know, everything is uniquely homotopic to everything else, but then you relax the structure and yeah, and by the way, there is a sign here. And this way you rediscover the bar differential. You rediscover the bar differential. And a lot of other differentials like the cyclic capital B and the Ginzburg-Schedler iota can be rediscovered from those considerations, same as the Gersten-Haber bracket and stuff like that. So you do have, yeah, 1 minute and I'm finishing. Okay, so let me just say that the last thing that I so for any those are also differential graded co-categories, and those are GG functors and everything is associative. So what I would like to say that Will is, well, the classical proof of the 60s, and then Will is non-commutative proof that actually crystalline cohomology is well defined, has a strengthening like this. What does it mean independent on everything. So those are kind of contractible. So you get a rigid structure, which is kind of everything is well defined up to homotopy. And let me just say, there are other examples, and I think it would be quite interesting to understand what is the overarching algebraic structure behind all that. Okay, so let me stop here. Sorry about going over time.
Thank you very much, Boris.
Thank you.
So I have several questions, but let's see if the audience step two. There's a clapping done, but I don't see any hands. Okay, so can you go back? Devarshi is asking through the chat, is there an analog of the Ginzburg-Schedler map in positive characteristic?
No idea. I don't know. Yeah.
So, but by the way, this is, I mean, I remember I saw this paper. You mean the paper, the Ginzburg-Schedler stuff you are citing is the one in this paper, free product cyclic homology and the Gauss-Manning connection with an appendix by yourself.
There was the second one as well, and frankly, yeah, what was where I can't say on the top of my head, but I think mainly it was in the first paper. Yeah.
There is a second question by Devarshi, which says, also does your last categorical result involve Q linearity of the category in any way?
What linearity?
Q linearity over the rationals.
No.
So the categories are not assumed to be Q linear.
Q, no, not at all, no. So it involves, for example, I mean, well, in commutative or in non-commutative case, you can write this, it's completely over Z. But, well, again, the Czech complex themselves are not interesting. They're interesting after you do something to them, like complete. So yes, that includes you complete, you know, with divided powers as they do in crystalline cohomology. Yeah.
So Yiling Wu asks, what's the motivation of taking commutators in the definition of the de Rham complex?
Well, I guess a lot of this non-commutative calculus is about traces, I guess, originally, you know, from the early 80s. First of all, again, maybe if you do Hochschild, even the original Hochschild homology, then the Hochschild differential happens to be the commutator, and it is good because it reflects, you know,
I mean,
kind of, I would say the prototypical formula of kind of even, you know, for matrix valued form, or the prototypical formula kind of from characteristic classes, whatever, is something like this. I would say that's the...
Yeah, well, I mean, I would add that modding out by commutators is like the Big Bang, because Cauchy homology is the derived factor of dividing by that. Cyclic homology, by your result in
Yes.
Decay theory paper,
Yes.
you get you take 3 ring resolutions and you model with it, you get cyclic homology. The result of mine that you cite is that if you divide by commutators and derive it in a different sense,
Yes.
or whatever, you get HP. So it's, I mean, it's the cause of everything. It's behind all the cyclic field. Yeah.
Yes. Yes.
Yeah. So I have a question concerning at a certain point that I got lost when you said you had this complex that was in the down, the half.
Yeah, kind of this one.
Yeah, and you said you get a quasi-isomorphism in every column.
Yes.
So you meant that I mean, you take the kernel of the first map that comes out of DR.
Yeah, let me
Because in the first row you had DR, right?
In the first row, I have DR. Yes, so here I have yeah, so here I have this. And here I have what, so by the way, yeah. Well, here it's not a problem. Yeah, both are.
That's an identity. Yeah.
Yeah, then I go here and it will be what? It will be. Correct. And here I will have. Yeah, so here in both cases, I get. Correct. Yeah, it's. I mean, they are the same. This short Hochschild complex, so to speak. Yeah. And the claim is that it happens. Well, first of all, that the Hochschild-Rosenberg map respects the columns and the rows, and already here it's it's not obvious.
Yeah, the point is omega 2, right? Because omega 1 is also omega 1 mod commutators is also C1 mod B.
Yes. Yes, yes, but yeah, so the first column, well, it is true, but the second column is also true, and it's less obvious. I mean, well, I guess it's still kind of obvious, kind of more or less clear. So it's omega t by the commutators, yeah, so by the cyclic group Z2. But again, well, even here, I think you need some proof. Correct, but they are, you know, same format, same. Yeah.
And you mentioned that at the beginning, the theorem of Karoubi, and that you will give a proof. You mean that non-commutative RAM is the image of the S operator in HC?
Yeah, but it follows. I mean, the cohomology.
You didn't mention it explicitly during the talk, or did you?
Yeah. But the cohomology of this complex, yeah, you can compute it explicitly, and well, again, it's basically, you know, the cyclic complex, but kind of perturbed a little bit by this factorization. Yeah, it's straightforward to prove that the cohomology of this complex is the kernel of S. Yeah.
And with regards to this thing that I did, there is some question that I had when I wrote this that I mean, at the moment I couldn't resolve, and then if instead of if you do not complete, right? So you take the complex, I mean the cosimplicial complex. You have an algebra A and you have a cosimplicial algebra.
Yeah.
In the end step, you have the n-fold coproduct. And you mod out by commutative.
Co-products in the ring sense, yeah.
In the ring sense, yes.
Yeah.
So at the moment, so I couldn't understand the field product in many variables. Then I wrote a paper with Castiglione where we understood it, but use it for some other purpose. And I never came to look into this. So I think that if you mod this out by commutators, it perhaps should give the RAM. I mean, the non-commutative, the RAM are Karoubi, as opposed to HP, because this is, I mean, if you believe that there is a perfect dictionary between these things and Grothendieck's infinitesimal, or what you call crystalline cohomology, then this should be an intermediate thing that he calls stratified cohomology, which in the smooth case, that is, in our case, if P is quasi-free, is crystalline, so it is HP, and we know that HP and the RAM coincide for quasi-free. So, yeah, maybe it should be true that if you mod this out by commutators, you get the RAM.
So what you are saying? Wait a second. What do you mod out by commutators?
But this is a cosimplicial ring, a cosimplicial algebra, right?
This one.
Yes. P is an algebra, right? So this is a cosimplicial algebra. And so every map that you wrote there is a ring.
Morphism of rings.
So it maps commutators to commutators.
Yes.
So you can mod out by commutators.
Correct, but aren't you doing this and completing and?
Yes, but but there is a I complete when I have a quasi. So you have a quasi-free. You have an algebra. You rate it as a quotient of a quasi-free one, and then radically complete, right? And this you get HP. Now HP is maps to non-commutative DRAM, that is to the universal DG algebra omega. Modulo commutators, but the map is not quasi-isomorphism unless the algebra is quasi-free in general. So I think this complex that you just wrote should always give, even if the algebra is not quasi-free, always give the RAM.
Oh, that's interesting. Yeah. It's kind of in the spirit. Yes. So you just don't, instead of doing this, you just take
P equal to A.
Yeah, I don't know.
Yeah.
It's kind of in the spirit of that. Yes.
Yeah, I think this is probably because at the moment, I mean, when I did this other thing, I used the fact that if P is quasi-free, then after completion, the Fedosov product coincides with the product of forms, which is easy
Correct.
to handle.
Yes. Yeah.
And I didn't know what to do with the Fedosov product of many variables, but then I wrote a paper with Castiglioni where we figured this out, organize. I mean, there is a way of organizing the product in the Fedosov product in many variables, and maybe using this, this can be kind of computation can be done, but I never carried it out. So.
Oh.
Maybe this should give someone motivation for doing this. Anyhow.
Yeah, yeah. And what was your growth index style like motivation? Why it should be so?
In the so in the you mean in the this exposés article, where he introduces all this, there is so he considers, so you know that infinitesimal is the cohomology of the structure sheet on the site, the Grothendieck topology whose objects are the infinitesimal, the nilpotent extension of and then you may also consider the nilpotent extensions which split by an algebraic homomorphism, and this topology is what Grothendieck calls the stratified site. And you can show that the cohomology of the stratified over the stratified site of the structure shift modulo commutators is the cohomology of this complex.
Is the cohomology what?
Of this complex, the one you just wrote. Is. And so and I think this should be the RAM.
I see, yeah. This makes a lot of sense, I think,
One thing I could never figure out is if you put coefficients, I mean, what to do with the, I mean, you can, if you have a bimodule with a connection and say the connection is, but if you have a bimodule with a connection that is flat in the rigid sense, then the module is extended from K, so it's not very interesting. But there should be a way of defining a connection so that you get on a bimodule that, I mean, not defining a connection, defining flatness in a way that if you somehow mod out by commutators, you do get an interesting complex. But I could never figure this out.
Yeah, I don't know.
Well, so it was very, very nice, very interesting talk, and thank you very much for mentioning my work.
Thanks. Yeah, that's a very good comment. Yeah. Okay, let me think about it. Yeah, it makes a lot of sense, I think, in the spirit of Ginzburg-Schedler. Yeah.
Okay, so I think we're done for today. I'm going to stop the recording.